All right. So, by the way, thank you all for joining this session. I know it's a Saturday afternoon, but I'm still seeing many people who have joined, and that's really encouraging. Um, so, before I actually get into the session, let me give you some background on what these online workshops are all about. Basically, we have our KCD Chennai conference next month on the 22nd on Saturday. So, as part of that event, we generally conduct pre-event workshops. So, we are actually doing both online workshops as well as in-person workshops. So, this is one such online workshop, and I am glad that you are here. Um, so basically, we this is our penultimate workshop. We had actually planned 8 workshops, so 6 workshops are already completed. This is our seventh workshop, and then we will finish it up with the final workshop on I think it's on yes, it's on July 8th. That is our final workshop. Okay, I think with that we can get started. I'll go to my presentation. Yes, I will just keep it in reader mode so that if there are any questions, I can go back to the Zoom window and then see if there are any questions. By the way, feel free to interrupt my presentation at any time. So if you have a question, you can either post it in the chat box, or if you want to ask your question verbally, just raise the hand in Zoom. Then I will unmute you and then you can ask the question verbally. Okay, so whichever way is comfortable to you, use that method. But every now and then I will be checking at the Zoom window so to see if there are any questions in the chat or to see if there are any raised hands. Okay, great. So today's topic is basically running machine learning models on Kubernetes. And especially this topic, basically, I wanted to especially select this topic because of the recent craze in machine learning and AI with the advent of things like ChatGPT, and not only that, even realistically speaking, there are many organizations who are currently leveraging machine learning in their products and solutions. Product companies, so even product companies who used to sell products, they are leveraging machine learning to augment their products features. I will give you one example. For instance, Ericsson is a telecom equipment provider, but Ericsson is currently leveraging AI in a big way for delivering energy efficient products. Typically, telecom products, especially in the RAN side, right, the radio access network side, they rely on huge amount of power, right? And companies like Ericsson, so they have actually developed a huge machine learning infrastructure and AI ML assets in order to reduce the energy consumption of these radio access networks. So that is one example. But overall, you can see that in many places, in many organizations, you will see machine learning and AI being adopted. Even consulting and services companies like Infosys, right? They are into using AI for intelligent automation, for automating many of their works and things like that. So slowly and steadily, machine learning will touch upon each and every one of us, either as a developer or as a DevOps professional or whatever profession that you are pursuing. So it will be very soon that you will be exposed to machine learning. And running machine learning models on Kubernetes is the topic that I have chosen, simply because Kubernetes has become the go-to platform. I mean, not only for cloud native workloads, you know very well that Kubernetes is widely used for running cloud native applications. Not only that, even machine learning models, Kubernetes is the de facto platform for not only for running machine learning models, even for doing your machine learning development work, right? So Kubernetes is the platform that is widely used for the development activities, for model training, for deploying the models, inferencing the models, and I mean throughout the entire life cycle of machine learning workflow, you will see Kubernetes being used throughout the the machine learning life cycle. So today I will be specifically talking about running machine learning models on Kubernetes. Okay, let me see. Yeah, that's fine. Okay, so I'm going to just switch off my video because I'm connecting from my home and I want to make sure that the bandwidth is okay. Fine. Let's proceed with the presentation. I'm Senthil. I am working as a principal software engineer in Ericsson. My role in Ericsson is architecting cloud native AI/ML platforms. These are large scale cloud native AI/ML platforms that are actually used by Ericsson's products and Ericsson solutions. Not only by products and solutions, these platforms are also used when Ericsson offers managed services to its customers. And apart from my day job, I involve myself in many community related activities. I am the organizer of the KCD Chennai conferences. This is our second conference. Last year we did an online conference. This year it's an in-person conference. I'm the maintainer of an open source project called as Kubefledged. Kubefledged is about caching container images directly on the worker nodes of a Kubernetes cluster. So this can be useful in situations like rapid scaling of real-time applications. So whenever the application needs to scale rapidly, if the container images are already available in the cache within the worker nodes, then it is very easy to bring up the scaled pods very quickly. So Kubefledged will help you in building that cache and help you in rapid scaling of applications and also rapid startup of applications. And I am a speaker as well. So I speak about Kubernetes and also the cloud native ecosystem and also on ML ops. And you can find me on Medium, Twitter, and LinkedIn. I tend to write some blogs as well, but not very frequently. I'm fairly active in Twitter and LinkedIn as well. Okay, let's proceed. By the way, the agenda, this is not the agenda. So agenda slide is not yet updated. Okay. So before we get into running machine learning models in Kubernetes, let us take a step back and really understand what machine learning models are. So a machine learning model is actually a software program. Okay. Uh, when you build applications, right? When you build applications in your work, normally what you do is this application is actually a program, a software program written in an high level programming language. So let it be Python or Golang or Java. So that is what you typically do in your applications, right? And machine learning model is also very similar to such applications in the sense machine learning model is also a piece of software. It is also a program, right? So someone has to write some code in order to develop a machine learning model. So at the end of the day, Machine learning model is nothing but a program. Okay. And that could be multiple, there could be multiple formats of delivering this program. So once a model is built, once a machine learning model is built, it can be actually built in different formats. So it could be like an serialized object. For instance, if you are developing an machine learning model using Python language, right? You can actually serialize the model into a pickle file. Okay. And there are various other formats in machine learning models, but still they are all programs. Okay. But they are all special kind of programs. So normally, typically, what you do in a program is you will have variables, you will have control loops, you will have decision making. So if then else, right? You will have looping, you will have for loop, while loop, and things like that, right? So those are all, deterministic way of programming. So deterministic way in the sense you very well know that if this is the input, this is the output that you will receive. Okay. The entire logic is actually coded using control structures like if then else or looping or whatever it is. Okay. But whereas a machine learning model is still a program, but the purpose of this program is it can find patterns, or it can even make decisions from a previously unseen data set. So generally what happens is when this machine learning model is built, it will be given an data set. Okay. That is called as training data set. So the model gets trained on this training data set. But whereas when the model is executing, and if you supply a new data set which is unseen by that particular model, it can still find out patterns in that data set and it can make a decision out of it. Okay. So here you don't have a fixed set of input and expect a fixed set of output, right? When you are training, you will have a set of training data, but whereas when the model is actually deployed in production, it can see data that is unseen by the model and it can still work. And that is what is actually expected out of the model. So this is what makes machine learning model a little bit different from traditional programs. And how the machine learning model is performing such predictions, or how it is capable of identifying those patterns, is basically because of the training phase. Because what happens is when the machine learning model is trained, it is actually supplied with a large data set, and this data set will have features or labels. Okay, this data set will actually be labeled, and depending on the labels, the machine learning model will actually adjust its algorithms. Okay, basically there is an algorithm, and this algorithm has various configuration parameters. So it will actually fine tune those configuration parameters based on the input data set, and this is what we call it as training. And once this fine tuning happens, then the output is called as the machine learning model. Okay. um, so as I said earlier, all machine learning models rely on an algorithm. Okay, there are various algorithms that are available in the machine learning world. Simple algorithm, complex algorithms, or even there are various different frameworks. Like TensorFlow is one prominent framework. There is scikit-learn, there is PyTorch. So all these are various different frameworks, and each of these frameworks provide you with some inbuilt algorithms, and they will also help you in writing your own algorithms. So training a machine learning model is actually choosing an algorithm and optimizing this algorithm for the specific input data set so that it can effectively find out patterns from this input data set. And all these patterns, the machine learning model will actually encode all these patterns or learn from the data, and then generate these patterns or the statistical distribution of the data. And then when a new data is applied to this machine learning model, it is actually capable of coming up with its own decision, right? So that's what makes machine learning models very special. and you will find machine learning models everywhere. So if you go to Amazon or Flipkart, so there are machine learning models used, recommendation models especially for you. They will actually recommend products. So this is all, this works based on machine learning. Google Maps, it works on machine learning. And anomaly detection in various tools, it also uses machine learning to a large extent. And machine learning is actually being widely used in various other scenarios as well. For instance, even in IoT. So when IoT devices capture data, uh, actually what is happening is machine learning models are running on the IoT devices itself or very closer to the device in the edge, so that where it captures the data and then it makes inferences out of that data, right? So slowly and steadily, machine learning is widely used in various other scenarios. Okay, so that's a simple introduction to machine learning model. Let me see if there are any questions. Okay, no questions. Right, I'm going to continue. Okay, this is ML model development life cycle. So the development life cycle of a typical machine learning model, it's better that we get an overview of how the machine learning model is actually developed, so that we can really understand what is the special use case that we are dealing with when we talk about running machine learning models on Kubernetes. Okay. So first of all, it is actually a loop. So here you will see that there is a loop. So let me get a pointer. Okay. So here you will see that it is actually a loop. Okay. And typically it starts with you defining or the data scientist defining the metrics and the acceptance criteria. So the metrics and the acceptance criteria are very important because that will actually indicate whether your model has been trained accurately. Okay. So you define metrics and acceptance criteria first, and then you gather the data. So whatever data that you can use for developing your model, you simply gather all the data, and this is where typically data lakes are used. Okay. And once you gather the data, then the data is actually cleansed. Okay, because the data can have some unnecessary data, or some data that is not fully complete. It can have incomplete data, or it can have some personal information, right? So in that case, the personal information has to be anonymized. So all these things are done in data cleaning. Okay, this is where ETL jobs will be run, and these jobs will actually act upon the data, and then it will provide an output data that is clean enough for the data scientist to perform machine learning model development. The next step is typically there is a data analysis and visualization step. There are special tools available to perform data analysis and visualization. There are specific Python packages available to do this. This will typically help the data scientist to visualize the data and then see, for instance, the data scientist or the data engineer might want to see the statistical distribution of the data. So looking at the statistical distribution of the data scientist can see what would be the best algorithm for such a statistically distributed data. Okay. What would be the best algorithm if the data is actually distributed in this fashion, right? So typically you use tools like cloud provider provided visualization tools, or you can write your own programs. Like it can be Spark jobs. You can typically people use Spark in data analysis phase and also in data cleaning phase. or there are plenty of tools available in these spaces nowadays. Okay. And then the development of the ML model commences. So this is where the data scientist will figure out what would be the actual algorithm to use, what framework to use, what libraries to use, what is the programming language that is best suited, and then finally develop the machine learning model. And in the training phase, all the cleansed data will be used during the training phase to train the model. And once the model is trained and the data scientist is actually satisfied with the accuracy of the model, then it is time to actually deploy the model. Okay. So until this point, it is actually very much development work. Okay. The data scientist will be involved, the data engineer will be involved, and the training of the ML. Once the training of the ML model is completed, then it is ready to be deployed. Okay. And this is where you will need specialized tools and frameworks to deploy the ML model. And this is going to be the focus of my presentation. So we will be more focusing on deploying the model and monitoring the model. Okay. So deploying the model in the sense, what are the good practices of deploying the model into Kubernetes? What are the frameworks that you can use for streamlining the deployment process so that it scales well, so that it becomes easy to monitor the model and things like that. Okay. So, and by the way, this is actually a loop. The significance of this loop is that uh, once you deploy the model into production, let's say, right, the model has to be continuously monitored for any drift situation. So if the model is not performing as per your expectations, if the models, for instance, when you initially started developing the model, you actually came up with some acceptance criteria, right? So you should constantly actually monitor the metrics from the model and see whether there are any drifts, which means the model is not performing well. So, and in that case, what you need to do is you need to actually figure out why the model is not performing well. And if required, the model has to be retrained. Perhaps because the distribution of the data that is actually coming in the production environment might not match with the distribution of the data that you used for training the model. So in that case, you will have to adjust the model. You will have to retrain the model with the new set of data. Okay. And then once again, you will have to deploy the model again. Okay. But in certain situations, you may also want to fine tune the algorithm itself. Okay. You may feel that the context of the model maybe it has changed. Okay. Maybe when you developed the model, you assumed a certain context, and that context might have been valid. But now, when the model has been deployed into production, and when it is running, there is a constant change in the environment, constant change. So because of that also, the model might not perform well, right? So in that case, you need to figure out what is the context change that has happened, and accordingly you may have to fine tune your algorithm, right? And so basically it's a control loop. I mean, you'll have to actually deploy it, monitor it, retrain it, and then deploy it, and then monitor it. That's typically how machine learning model life cycle is. Okay. Okay, so there are a couple of questions, so I will take these questions. So Ashok wants to understand, can you once again explain what is the purpose of visualization here? Yeah. So, okay, so machine learning model basically relies on data. Okay. The algorithm part of the model is actually well known. Okay, these algorithms are existing for years together. Okay, and many of the programming languages they provide you with ready-made libraries for working with various types of algorithms. Okay, but what really is the challenge in machine learning model development is the data. Okay, data can come in various formats. So here you see data could be in SQL format stored in an SQL database, or it could be a NoSQL data like key value store, or it could be an totally unstructured data. For instance, if it is an audio file or it's a video file, right? This is totally unstructured data, right? So you have the challenge of dealing with a huge amount of data here, and that two different types of data. Okay, so here you'll see it's a huge amount of data, and you also need to deal with different types of data, right? So it helps to visualize the data first before you actually come to a conclusion on what would be the best fit algorithm. Okay, for instance, if I want to do a statistical distribution of the data points, right? Let's say I draw an x-axis and then an y-axis, and then I want to distribute the data points statistically and then figure out what is the mean and figure out what is the standard deviation, right? So data visualization tools can help you here. So it can easily help you to graphically visualize the data and then even analyze the data, and it can even help you to modify the data and then see what is the bearing it has on the mean and standard deviation. So almost always before you enter into developing ML model, before you actually start writing the code for the ML model, there is a considerable amount of effort that you need to spend in analyzing the data and visualizing the data. Okay, only then you will know what exactly is the algorithm that you need to use, what exactly are the hyperparameters that you need to use to start with, and then things like that. Okay, so data visualization can help you a lot in actually reducing the effort that you spend in iterative model development. Okay. I mean, but if the data is very straightforward, then probably you may not need to visualize it, but definitely the data will be huge if for any meaningful machine learning model development work. The amount of data that you will have to analyze and visualize is huge. So data visualization will help you here. Okay. So there is another question from Shankar. So Shankar wants to know, the model keeps evolving, right? What is the frequency that we have to do retraining? Okay. That's actually a very good question. Um, so the model always keeps evolving. Okay. um, this is unlike traditional software, because traditional normal applications, you know very well that when you supply and this input, okay, based on the logic coded in the program, this will be the output. Okay, but machine learning model, that is not the situation, because machine learning models are actually trained using a data set, and once deployed into production, this data set will change. Okay, the data that the model is seeing in the production will always be a new set of data, right? So naturally what happens is the model needs to evolve. Okay, so naturally you may have to retrain. Okay, so there are different strategies for retraining the model. So one simple strategy is you retrain the model every week, okay, or every month. So this is you actually, what you do is you will keep storing the data in batches. You will store 1 week of data in a batch, and then what you do is at the end of this batch you retrain the model, and then you deploy the model. And then similarly, once the model is deployed, then you start storing the next batch of data. That is for the next week. Okay. So this is typically the case when you have a steady stream of data coming into the system, and in that cases you can simply choose to retrain your model for based on the fresh set of data. Okay. There are also advanced strategies wherein you will actually accumulate all the data and then do a complete cumulative data distribution. You use the cumulative data to train the model, or there are also mechanisms wherein you can use a trained model and then the delta of the data to get a new model. Okay, so there are various scenarios possible, but the simple scenario is you retrain the model every week or every month. Okay, but if at all you want to actually really see whether the model is performing well, and only then only when the drift is happening, if you want to retrain, then you will have to do some active monitoring of the data, active monitoring of the model. Okay, so there are mechanisms available in order to identify whether the model is drifting or not. Okay, so there is something called as alibi detect. So that will actually help you to figure out whether the model is drifting or not. So if the model is drifting, then it means that the model has to be retrained. Most likely, the model had to be retrained. Then what you do is you collect the fresh data set and then you train the model. Okay, or sometimes what you may have to do is you will still use the existing data set, but you may start with a different set of hyperparameters for that particular model. Okay, which means then the model will end up in a different the model will start with a different set of hyperparameters, and then based on the tuning of the hyperparameters, then you will get an entirely different model. This is basically need-based model training. So simplest form is in a regular frequency, you keep training your model, you whether the drift happens or not, but that is applicable only when you have a steady stream of data. And in certain scenarios, this will not be feasible, or this might not make sense. Then that is where we will have to monitor for the drift in the data set, or the drift in the model accuracy itself, and then take a decision to train the model. Okay, fine. So let me continue. All right. So here I'm going to actually explain how data, model, and code uh, is actually used or generated in the various steps of the ML workflow. Okay, so I have different pieces here. So the first one is model building. The second one is model evaluation and experimentation. So evaluation and experimentation is once you build a model, you evaluate whether the model is performing well or not. This is where you will determine whether you are satisfied with the accuracy of the model. Okay. Next is productionize the model. Productionize the model is once you have the model program built, then then the next step is to productionize the model. Productionizing the model is basically you make the model fit for deploying into production. Okay, it can involve many things. For instance, if it is a deep learning neural network, right? Productionizing can actually involve optimizing the number of layers in the neural network, right? Because if the number of layers in the neural network are too high, then the performance of the model will come down. So productionizing can actually result in optimizing the number of layers in the neural network, or it could be like you bring down the size of the model, right? There are tools available which can actually read the binary and then reduce the size of the binary, Or it could simply mean, or it could actually simply also mean that you build a container image out of the model so that you can actually deploy the container onto Kubernetes. So productionizing can mean different things in different scenarios. And once the productionizing step is completed, the model is tested before it is actually deployed. And then once deployed, it is actually continuously monitored. Okay. So what happens in model building is there is a training code and there is training data. So using the training code and the training data, the data scientist comes up with a list of models. Okay. These are called as candidate models. And all these candidate models are evaluated using test data, right? So you see test data here and using metrics. Okay. So using the metrics from each of these models, the data scientist would be able to figure out what is the best model out of all the candidate models. So that is the chosen model here. Okay. So this model is now chosen for deployment. So next step is to productionize the model. So different techniques are available for productionizing the model. So once the model is productionized, then the model is tested. So again, what happens is there is a test code and then there is test data. Okay. So the test code will actually use the productionized model as well as the test data and then see whether the model is actually still performing well. Okay. So whatever metrics that you are, even here, the metrics will be collected and then the accuracy of the metrics will be checked. And finally, the model is ready and the model is now ready to be deployed into Kubernetes. So this is actually called as model serving. Both the deployment as well as the monitoring together, we call it as model serving. So actually what happens here is here you have the application code. Okay. So training code is basically used for training the model. Okay. And then that code will not be used at all. This training code will never get into the model. This training code will never get deployed into production. Okay. Similarly, this test code is only for testing the model. It will, again, this test code will never enter into production. Okay. So in production, you will have application code. The application code is actual software, actual traditional software, which will actually rely on this model for some specialized capabilities. Okay. For instance, if this application wants to perform anomaly detection, okay, then there is an anomaly detection model that this application code will use. Okay. So you have a model and then you have an application. So both the model and the application code are deployed in this case to Kubernetes. Okay. Both I'll talk to you about how the application code runs and how the model runs in a typical deployment scenario. Okay. So eventually what happens is the model is getting deployed into production and then the monitoring also happens. Okay. So once the deployment is completed successfully, the monitoring is also happening. So for this monitoring, the data in the production setup is used because this model was actually developed using an algorithm as well as a huge amount of training data, right? So the training data, this model has consumed a huge amount of training data during the training phase. Now, once it is deployed into production, this model will be constantly monitored based on the production data. Okay. So production data is the actual data that is getting ingested into the production system. Okay. And this application and the model are part of this production system. So with this production data, how is the model performing? That is what is actually performed in the monitoring phase. Okay. So in the monitoring phase, if there is any drift, okay, if the drift could be like the drift could be in the data itself. While training the data, maybe the statistical distribution was different, But when the production data is analyzed, maybe that statistical distribution is different, which means the input data that is now fed into the model is facing a drift. It is no longer conforming to the statistical distribution of the training data. So this is actually a drift, and the monitoring system is capable of identifying this drift. Okay, so the deployment as well as monitoring both together constitute the model survey. Okay, and this is something that is very important for us to know, because in an ML system, the deployment is also important, and also the monitoring of the model drift is also important, because if the model has drifted, right, and you don't replace the model, then the application would be relying on wrong prediction from this model. So it won't be actually performing its intended requirements anymore. Okay, so this is another challenge with using machine learning model. So you have to constantly monitor the machine learning model for any drift, and then you will have to constantly retrain the model. Okay, in some situations you may not face drift at all. Okay, in certain situations where the data is very deterministic, you know that this is the pattern of the data, right? In those situations the model would still continue to perform for months together, right? But in typical situations that is not the case. The model will always face a drift, because there will always be some changes to the data or some changes to the environment in which the model is running. So depending on that, the monitoring system will tell you whether it is time to retrain the model. Okay, all right. Any questions, guys? You understand, or you want me to repeat anything? All right, I think it's clear. Okay, good. So let me now proceed. This is a very interesting picture. Um, this is often actually quoted in any machine learning course that you will take. Okay, this is actually a very interesting and an important depiction of the unique characteristics of machine learning. Okay, this picture was actually first published in one of Google's paper called as Hidden Technical Debt in Machine Learning Systems. So basically what the authors did was they actually made an analysis. Okay, they were actually analyzing what are the different important pieces for developing machine learning systems. Okay, and what they found out is that the actual machine learning model, so here it is actually denoted as machine learning code. So what they actually figured out, and they were also able to prove, is that the actual machine learning code is only a very small portion of the larger machine learning system. Okay, and the reason is, for this machine learning code to function well and for the users to actually benefit from this machine learning code, there are multiple other pieces that need to work together, and these other pieces play a huge role in the successful development of machine learning systems. So here you will see that data collection consumes more effort, okay, than developing the machine learning model. I mean, these boxes actually refer not only effort, but also the importance, but also the cost and things like that. And data collection, feature extraction. Feature extraction is basically a step that is required for generating a training data set. Okay. And then data verification. And then finally, you see here serving infrastructure. So this is the one that I wanted to highlight here. So you see the serving infrastructure as well as monitoring. So they also form a huge portion of machine learning systems. So there is a huge amount of effort as well as cost that is involved in building these serving infrastructure and monitoring systems, maintaining them and scaling them, So the what actually makes this picture very important is that uh, whenever you do a course on MLOps, for instance, right, you will almost always see this picture being presented. This shows that this is where the data scientist work is. Okay. So what happened to my pointer? Okay. So typically the data scientist would be actually involved in developing this machine learning code. But what about all these other pieces, right? The serving infrastructure, monitoring, configuration, analysis tools. So all these things require software engineering, which means developers, software engineers, DevOps professionals, machine learning engineers. So all these other different teams and skill sets have to come together in order to make the machine learning code deployable and successful in production. Okay. So that is where actually the serving infrastructure gains more prominence. And this is where actually running machine learning models in Kubernetes is actually very important. Okay. Um, Fine. So let me see if there are any questions. Okay. Not for now. Good. And if you see, there are plenty of tools available nowadays for machine learning for each and every piece of this. For instance, for serving, right? There are lots of frameworks and tools available. I will be actually talking about one open source framework in this presentation, but there are lots and lots of frameworks available. For instance, Google has its own framework called as TFX. I mean, I shouldn't call it as Google's own framework. It is actually a TensorFlow native framework called as TFX, TensorFlow Serving. And then you have something called as Kubeflow Serving. There is something called as KF Serving. It was called as KF Serving, and then now it is called as KServe. So Kubeflow has its own framework for machine learning models serving, and MLflow has its own, serving framework. And for instance, NVIDIA has its own serving server called as Triton Inference Server. So many vendors have different types of serving infrastructure. Similarly, for monitoring, there are different solutions available. So Alibi Detect is one such solution, and you have monitoring capabilities provided by different libraries of Python itself. Okay. So for each and every piece for data collection, so you have many different solutions here for collecting data, for ingesting data, for storing the data in data lake, and then for building data pipelines, you have things like Airflow, you have things like Dataflow, you have Apache Beam, you have Spark, and all these other tools. And machine resource management, then for instance, if you use specialized hardware resources like FGPAs, or you use um, TPUs, tensor processing units. So all these specialized hardware resources are now readily available in public clouds. Okay. If you need GPUs for training your model, so all these resources have to be managed effectively. So you need resource management, right? So if you see, there are plenty of tools available in the machine learning space, each catering to one of these different needs. Right. I think I saw a question. Okay, there is a question from Karthik. Can the training data set be a historical production data, or typically it has to be cooked up in lower environment? Typically it is historical production data, because you need to, because the success of the machine learning code here, right? The success or the accuracy of the machine learning code is directly proportional to the quality of the data as well as the amount of the data that you have for training the model. So, uh, so the preferred data set is always historical production data. Okay. And this is the data that will be preferred for developing the machine learning model. But there are situations where you won't have historical data, or the system might be producing this historical data, but this data might be owned by some other party. So if you are developing a product and if you are selling a product, right, the customer has bought this product from you, and the product might be emitting huge amount of data, and the customer might be storing all this production historical data in a, let's say, in an S3 storage, right? But you as a product, or but you as a person who sells the product or develops the product, you may not have access to the data. Okay. So in that cases, what you will do is you will actually come up with something called a synthetic data. Okay. So these are data that you extrapolate based on available data. Okay. And then you come up with an training data set based on this synthetic data. Synthetic data is actually, there are also techniques available on how to produce accurate synthetic data. So these are actually data that you actually produce, and you can also develop machine learning models for generating the synthetic data. And there are various techniques available. So that itself is a different field, a niche field in machine learning, on how to generate synthetic data. Okay. So yeah, so there are two different ways. So one is the training data set is typically or preferably comes from production data. That is always the ideal case. But sometimes you may also have to work with synthetic data. Okay. And not only the serving infrastructure, here you will notice that monitoring is also, very, very important here. By the way, monitoring is equally important in our applications as well, not just in machine learning, because even in applications, you may have to constantly monitor the metrics, right? The metrics could be like simple metrics like CPU consumption or memory consumption, right? Resource consumption based metrics, or it could be like traffic and load based metrics, or for like latency. What is the latency of the requests, or what is the throughput of the requests? Okay, that your application is able to withstand. Okay. And likewise, there are various metrics that you may have to constantly monitor. But in the machine learning world, the monitoring actually takes a bit of more significance. Okay. That's simply because if you don't constantly monitor, then you run the risk of using a drifted model. Okay. Which means once the model has drifted, the output from this model is no longer reliable. Okay. For instance, if you are using Google Maps, right? And if the models behind Google Maps have drifted, then probably Google Maps will show you a wrong route. Okay. And that is really, really, really bad, right? So we should not, and systems, as developers and people who are actually maintaining these systems, we cannot allow that to happen. Okay. So constantly monitoring the machine learning models for drift is very, very important in machine learning systems. And that is actually very important here as well, both serving as well as monitoring. So I will be actually talking about an open source framework called as Seldon-core. So that supports actually that basically supports serving, okay, deploying the machine learning models and inferencing the machine learning models. But there is also support for monitoring, that is called as alibi detect. Okay, that helps. Alibi detect is basically a library that Seldon provides you. So using that library, you can develop monitoring application, which will help you in identifying the drift, whether the model has drifted or not. And it can help you to generate notification like cloud events. It can generate cloud events notifications to actually specify whether a drift has happened or not. Okay, let's proceed. All right. So, as I said earlier, I will actually talk about an open source project. It's called as Seldon-core. The company behind this open source project is actually called as Seldon, and the name of the open source project is actually Core. It's simply called as Core. We use the term Seldon-core to refer to this project. Okay. And this actually helps in running machine learning models in Kubernetes. I'm going to actually talk to you in detail about what I really mean by running machine learning models in Kubernetes. So what is the significance, or what is the USP in running machine learning models in Kubernetes, and where actually the Seldon-core project fits in, right? So first of all, we need to basically understand. Let me ask myself a question. Do I really need something like Seldon-core? Do I really need a new framework or a platform like Seldon-core for running machine learning models in Kubernetes? Because right, we know that machine learning model is nothing but a program, right? It's actually a binary, okay? And we know very well how to build container images based on binaries, and how to run this container images in Kubernetes. So we all are well versed with that. We know how to write a Docker file. We know how to package this binary into a Docker image by installing all its dependencies and things like that. So the what is special about Seldon-core, or what is special about these frameworks that are actually used widely in running machine learning models in Kubernetes? So I'm going to demystify this, and then I'm going to actually tell you what is the advantage that you get in using frameworks like Seldon-core for running machine learning models in Kubernetes. So let's continue. Any questions, guys, before I delve into Seldon-core? Because for now, till now, we have actually spoken about machine learning models in general. What is the special characteristics of machine learning models, and the importance of serving infrastructure and monitoring when these models are deployed into production. Okay. So from this point onwards, I will be actually entering into Seldon-core. I'll be explaining more about where Seldon-core actually fits in, what are the advantages of using Seldon-core, how to actually work with Seldon-core, what are the components of Seldon-core, what is the CRD that Seldon-core provides. I'll actually explain you how to write your own custom resource for deployment, and I'll actually install Seldon-core in a Kubernetes cluster, and I'll actually show you a demo of deploying ML model onto a Kubernetes cluster. Okay, fine. Let me see if there are any questions. All right. So Nimish asks a question. So Nimish wants to know, is there any benefit of training models on Kubernetes? Yeah, that's a very good question. Um, if you see, when data scientists started out with, you know, developing machine learning models and training machine learning models, so data scientists, they are not very comfortable with Kubernetes. Even now, data scientists are not comfortable with Kubernetes. So typically, a typical data scientist would actually, what they do is they uh, procure a local machine. Okay, so if they are working in a laptop, what they do is they procure a physical machine. They connect that physical machine to their local network. So that physical machine will have the will have all the necessary hardware like GPUs or TPUs, and they prefer to train their models on those machines. Okay, so that is still existing, but that is not a scalable solution, right? And that is not a cost optimized solution. So how can you just procure a huge physical server and then allot it to a single person? Okay, so naturally, nowadays, training of machine learning models happens on Kubernetes itself. Um, Kubernetes provides you with specialized resource management capabilities for the specialized hardware. So if you need GPUs for training your machine learning models, so GPUs can be actually exposed as a node resource, worker node resource in Kubernetes. Similarly, FGPAs. Okay, so all these resources can be managed by the Kubernetes scheduler as well as kubelet. And if I remember, in a very recent release of Kubernetes, there was a feature to to manage any arbitrary hardware resource. Okay, very similar to CNIs and CSIs. So CNIs is basically container network interface for you to arbitrarily manage any type of networking solution. Similarly, CSI helps you to manage different types of storage solutions, right? In an using an uniform interface. So similarly, it is now possible to uniformly manage any type of hardware resources, hardware computing resources like GPUs or TPUs or FGPAs, using an uniform interface in Kubernetes. Okay, so so training a machine learning model makes more sense when you run the training job in Kubernetes itself. So Kubernetes itself provides you with the jobs native resource. So for running batch jobs, training typically are batch jobs. Okay, so you can make use of Kubernetes jobs, or you can make use of, for instance, you can run Spark jobs for training your machine learning model. Or if you want to build more elaborate, comprehensive pipelines for training your machine learning models, you can use projects like Argo Workflow, or you can use Kubeflow pipelines. So different pipelining tools are now available in Kubernetes. So Kubeflow pipelines is available. Likewise, you have Flight. Flight is another pipelining tool. Even TensorFlow also has its own pipelining tools. So likewise, training models in Kubernetes is now much more easier because Kubernetes itself has very good support for managing resources required for training data sets. And Kubernetes has plenty of tools, not Kubernetes, I mean, the Kubernetes ecosystem has plenty of tools to help you in defining and running pipelines. So it makes perfect sense to run your training jobs in Kubernetes. And even there are specialized frameworks available on top of Kubernetes to run your batch jobs. So you no longer need to work with the limitation of the jobs native object. But recently there is a lot of improvement that the Kubernetes upstream project has made to make the jobs more robust, right? So lots of developments are happening in Kubernetes itself to make many different workloads possible in Kubernetes. So definitely 100%, even 200%, it makes sense to run the training jobs in Kubernetes. Okay, let me see. Yeah, that's all. All right, so let's continue. Okay, so I was talking about Seldon-core. Okay, so what essentially is Seldon-core? Seldon-core converts your machine learning models or language wrappers. So I will talk about language wrappers later in the presentation. So it basically converts your machine learning models into production microservices. Okay, because finally you will have to deploy the machine learning models as microservices. Okay, that is the most preferred and prominent method of consuming the machine learning models, running them as microservices. So there are advantages of consuming machine learning models in the form of microservices. You get all the benefits of microservices, and it will easily fit into the larger application framework. So if your application is a microservices application, right? And if this application needs to consume machine learning models, then naturally it makes sense to deploy the machine learning model also as a microservice, right? And that is mostly the case. Okay, mostly machine learning models are deployed as microservices. Okay, and the application that uses the model either uses REST or the gRPC client to access the machine learning model. Okay, and Seldon-core will easily convert your machine learning model into microservices. So that is actually, in a nutshell, that is what Seldon-core does. Okay, this is the crux of Seldon-core. So if you have a machine learning model, so you as a data scientist, if you have actually built a machine learning model, and let's say you have stored the machine learning model in an object store like S3 bucket. So from that point onwards, Seldon-core will take the model, it will convert that model into a full-fledged server, and then it will deploy the server as microservice inside Kubernetes. Not only that, you can also manage the scaling of these models. It will also expose the model you using any supported exposure framework like Istio or Ambassador. And not only that, it can also expose metrics about that model. Okay, you no longer need to scrape the metrics directly from the model. You can actually rely on Seldon's uniform endpoint, metrics endpoint, for you to scrape metrics, custom metrics from that model. And you can also actually build inference graphs using Seldon-core. So not just, I mean, in typically what happens is you won't actually rely on a single model. You will actually perhaps rely on multiple models. Sometimes you may have to combine the output from these models. You may have to transform the output of from these models and then feed it into a different model, right? So so if your deployment if you have some advanced deployment scenarios, Seldon-core makes it easy for you to implement these advanced scenarios. So the crux of Seldon-core is, as I said earlier, it helps you to convert your machine learning models into microservices. But then it also gives you all these other capabilities like exposing the metrics, like being capable of scaling the models. It supports manual scaling as well as horizontal pod autoscaler based automatic scaling. It will help you in building these inference graphs. Okay, that is actually very useful. So this is basically Seldon-core is an open source framework that lets you deploy your ML models on top of Kubernetes. Okay, and it is actually a very widely used framework. You can check up their GitHub project. It is actually a very popular serving framework, open source framework that lets you run machine learning models on top of Kubernetes. So it has support for REST as well as gRPC microservices. And they also support a wide variety of machine learning model frameworks like TensorFlow, PyTorch, and any machine learning model framework uh, uh, that is widely used is actually supported by Seldon. So out of the box, they provide support for TensorFlow, Scikit-learn, PyTorch, and all these famous machine learning frameworks. And Seldon also provides you with language wrappers using which you can write your own models. Okay. Um, these are not like Python libraries that are used in machine learning model development. Rather, these are language wrappers for you to write your own servers. Okay, for you to write your own servers which will actually run as microservices. So we will talk about what I mean by this later. Yeah, I mean, at the core, it is actually a tool that helps you to convert your machine learning models into microservices, but it provides you with much more than that. Okay. Okay, fine. Good. So let me continue. Okay, the time now is 3:40. Maybe we will take a break at 4 o'clock. Okay, I will continue for another 15 minutes and then we can take a break at 4 o'clock and then we can resume at 4:15. Okay. All right. So this picture is what to say, it actually provides you a good overview of what Seldon-core is all about. Okay. I perhaps will spend the next 15 minutes explaining you this diagram. So this is a diagram that basically gives you the complete picture of what happens in end-to-end model serving with Seldon-core. Okay. For now, I am going to draw your attention to this rectangular box here. Okay. This rectangular box is basically a Kubernetes cluster. Okay. Your typical Kubernetes cluster. And Seldon-core actually runs as a Seldon-core controller here. Okay. So there is a controller that runs here, which also acts as the operator. And apart from this controller, Seldon also defines a CRD. So that is what you see here. Okay. So this is called as Seldon deployment CRD. So whenever you want to deploy a machine learning model, you write a CR like this. Okay. So I am not going to get deeper into the contents of the CR now because I will be covering that in a special slide. But for now, understand that there is a controller and then there is a CRD and you have to write a custom resource every time you want to deploy a model. Okay. Now, these other boxes, right? Metrics. So metrics, Prometheus is a well-known metrics server. So the message that is shown in this diagram is that whatever model that you deploy, right? So that is what this picture is. This is actually the running model. But I'm going to explain to you why there are various different boxes and what is the meaning of these different boxes. But on the whole, this is the deployed model. Okay. So this deployed model will emit metrics, right? So these metrics can easily be scraped by your existing Prometheus server. Okay. And not only that, the traces, if you are using distributed tracing, if your model is emitting distributed traces, these traces can easily be collected by Jaeger. Okay. It can be Jaeger native traces, or it could be OpenTelemetry traces, whatever it is. This can be easily collected by Jaeger. Okay. Now let me go back to this part of the diagram. Okay. So there is a data scientist here. Okay. And there is a software engineer here, right? So typically it is a role of the data scientist to develop the machine learning model. So in this case, the data scientist is actually uh, doing the model development. So as part of the model development, the data scientist has come up with the final version of the model. Okay. So it can be developed using various frameworks. It can be developed using any framework. Okay. So Seldon-core supports models that are developed using any framework. It can be scikit-learn, it can be TensorFlow, it can be, so this is scikit-learn, this is TensorFlow, and this is MLflow, this is XGBoost. Okay, so all the different frameworks are supported. Okay, and finally, the model is stored in a central repository. So this central repository can be of different types. In this case, let's say it is an S3 bucket. Okay, because the model is actually an binary, so it could be a binary, or in some frameworks they also support files like JSON files. The model can be in the form of a JSON file. Okay, but typically it is a binary, and the model is actually serialized and then stored as an object in an S3 bucket. Okay, so now the data scientist has completed his or her job. So the data scientist has developed the model and pushed the model. So at this point, the model is actually residing in this repository. Okay, now step number two, now the software engineer kicks in. Okay, so now the role of the software engineer here is to create what we call it as model server Docker images. Okay, you remember in the previous slide, maybe I'll go to the previous slide. See, Seldon-core actually converts your ML models into production microservices. Okay, so every microservice actually will require a server, right? So for instance, if it is a Golang, then there are specialized frameworks available for you to develop your own REST servers, correct? Similarly, Python, that is, Python has something called as what is it, Unicorn or something. So whatever it may be, you need a server. Okay, so for if it is a REST, you need a REST server. If it is a gRPC, you need a gRPC server. Okay, so basically what the software engineer does is the software engineer prepares model server Docker images. Okay, and again, these are not, plain vanilla REST servers or gRPC servers. These are specialized servers because they have to actually understand this model. Okay, so if this is actually a scikit-learn model, then this has to be a specialized scikit-learn server as well. Okay, or if it is a TensorFlow model, then this image has to have the TensorFlow libraries. Only then it will be able to run this TensorFlow model. Right. So basically, the software engineer builds model server images. Okay. So for instance, if the organization is using TensorFlow and scikit-learn, okay. So the software engineer will develop two different model servers, one for scikit-learn and another for TensorFlow. Okay. So typically, this is what a software engineer's role is in model serving. They provide model servers. Okay, and not only that, they keep constantly updating the model servers. They keep tweaking the model servers. If there are new dependencies required, they keep updating the Docker images, and sometimes they even constantly change the base Docker image. So if there is a new version of the base Docker image available, then they constantly have to uplift their Docker image to use the latest base OS Docker image. So, so this is an ongoing software engineer work. And similarly, there is an ongoing data scientist work to actually constantly train and retrain the model, let's say. So the model actually resides here, and then the model actually resides here in an S3 storage, whereas the model server image actually resides in a image registry. Okay. Now, let's see what actually happens when the model is deployed. So now the model is available in S3, and then the model server is available in the Docker image. Let's assume the Seldon-core controller is running. So the moment I decide to deploy my model, what I do is I create a Seldon deployment manifest. Okay, and then I simply say kubectl apply -f, the file name of this manifest, right? So the Seldon controller will pick this manifest, and then it will create all the necessary Kubernetes resources. So in this case, what it will do is The Seldon controller will create a Kubernetes deployment, and this deployment will eventually result in the creation of a Kubernetes pod, and it will also create a Kubernetes service for exposing the pod, right? So all these Kubernetes resources are created by the Seldon-core controller. Okay. And speaking of the pod, right? Speaking of the pod that the Seldon-core creates, the pod will actually use one of these images in the image registry. Okay, so that's what you see, the server, right? So this is actually a container. So the pod will actually have two containers. So remember that. So the one of the containers is actual model server, and this container will have the model downloaded and mounted as a volume onto the server. Okay, so that will be performed by an init container. So there will be an init container which will actually download this model, put it in an volume, and then mount that volume inside the server. So the server now has access to the model, which means once the server starts up, it will read the model, and then it is now ready to serve prediction requests. It is now ready to serve the model. Okay, so here you have the model, and here you have the server to serve the model. Okay, so now we are ready to serve the model, but not yet, because there is some other magic that is done by Seldon-core. So Seldon-core not only creates this server, it also creates an orchestrator. Okay, this is either called as Seldon engine or Seldon executor. Okay, you remember I told you in the previous slide that though the crux of Seldon-core is to convert the machine learning model into a microservice, it also helps you in defining these inference graphs. Okay, I will actually explain you about these inference graphs. So this inference graphs will help you in things like if there are multiple models, it will decide to which model the request has to be routed. It can do things like transforming the data before it is actually passed on to the model. And this also actually really exposes a uniform metrics endpoint for all the models. Okay. So all this thing is done by the orchestrator. It basically orchestrates the inference graph that you provide. So here you see the term graph, right? So basically this orchestrator orchestrates the graph that you specify in the Seldon deployment. So this is a second container that is running inside the pod. Okay. So the image for the second container is entirely provided by Seldon. Okay. Whereas this model server Docker images are built by the software engineer, but then Seldon also provides you with its own pre-packaged model servers. So if you want to use some readily available model server, you can still use that. Okay, but sometimes you may have to actually tweak it a little bit in order to provide additional capabilities. But Seldon also provides you with readily available servers which you can use it. But at the end of the day, this is what happens. Okay, so there is a Seldon-core controller, there is a CRD, and then there is a model that resides in the repository. There is a model server image in the Docker registry. And then once I deploy the model by applying the Seldon deployment manifest, Seldon controller creates a pod, and this pod can have multiple servers depending on what I specify in the graph. Okay. Sometimes it can also result in spinning up of multiple pods. Okay. So those are all advanced concepts. I will not talk about those advanced concepts now. So it results in the creation of a pod, and then there is a server running, there is an orchestrator running. Okay, so basically you see the data scientist has given you the model, and then there is a model server image that needs to be built. That is all. Okay, the rest of the things are taken care by Seldon itself. Okay, so you don't have to necessarily download this model image and then put it into the model server Docker image and then package it and then deploy it as a deployment. I mean, what will you do if you want to do inferencing the way that Seldon has defined, right? So if there are multiple models and you want to distribute traffic across these different models, right? So out of the box, Seldon-core provides you an easy solution. So so you get this model serving. So all you need to do is develop this model and then have your model servers ready in the Docker images. That is all. So then once you create the Seldon deployment manifest and apply it, the models will be deployed and then it will be ready for serving. Okay, let me see if there are any questions. Okay, fine then. Any questions, guys? Is it clear what is the role of Seldon-core in model serving? So at the end of this presentation, you will walk away with a clear understanding of basically what a machine learning model is and what it means by running machine learning models in Kubernetes. Perhaps you will feel that, okay, it's not that big a deal running or deploying machine learning models onto Kubernetes, or perhaps you may feel that, oh, you may, oh, there are so many things that I need to take care when I need to deploy a machine learning model onto Kubernetes. Okay, so whatever it is, at the end of this workshop, my goal is to demystify running machine learning models in Kubernetes. So either you may feel that it is not a big deal, or you may feel that there are so many pieces to it that you may want to learn more about model serving and things like that.
Here, one quick question, like here we need to install locally Docker and Kubernetes or how it works, just
Yeah,
curiosity.
yeah. So you need a Kubernetes cluster, definitely. So you definitely
Okay,
need a Kubernetes cluster, and you need a Docker registry where you push your model server Docker images, and you need an S3 storage to store the model. Or you can actually decide to have the model in your source code repository itself, and then directly fetch the model and then, build a Docker image out of that model. So that is also possible. Okay, but
okay,
typically
okay,
you want to decouple these two things, okay, because you don't have to, because then when you start packing your models also into the images, then every time the model changes, you will have to rebuild your model servers.
okay,
So you may want to avoid that. So definitely you will need a Kubernetes cluster. I'm going to actually show a demo. So I'll
okay.
be showing a demo of Seldon-core on a remote Kubernetes cluster, but you can do the same thing on your local Kubernetes cluster also, where like MicroK8s or Docker desktop.
Okay, okay, yeah. Sounds good.
Yeah, I have one question now. So you mentioned Seldon-core converts the machine learning models into production microservices, right? So in this diagram, where does it convert into a microservice? Right in
Yeah,
this.
yeah, very good question. Very good question. Okay. See, the model is residing here, right? So the model is actually residing here in an external repository. It's residing external to your Kubernetes cluster, right? Similarly, the image registry is actually holding the model server's image. Okay. So Seldon is actually the glue here, which actually combines these two things and elegantly comes and elegantly deploys a server, a microservice here. So you see this container here, right? So this is the
Mhm.
microservice.
Okay.
So it's the job of Seldon-core to convert the model into a microservice, and it is actually the microservice is nothing but this container that is running here.
Okay.
Okay, so you don't have to every time when you see every time when you develop a new version of the model, you don't have to rebuild your container image at all. So that will be taken care by Seldon because the init container. So I mentioned about the init container, right? So the init container will actually fetch the model from the repository. It will load it into a volume and then mount that volume onto this container. the server container. And not only that, Seldon also will actually expose this microservice onto either Istio or Ambassador. So natively it supports Istio and Ambassador. So if you have Istio or Ambassador, it will also expose the microservice. If it is Istio, it will expose it using a virtual service. If it is Ambassador, it will actually expose it using annotations on that service. So you also get automatically the model service also gets exposed automatically, right? So that is what is happening. So you start with the model in the repository, and then Seldon takes care of the rest of the things to convert that model into a microservice.
Okay, yeah. Thank you.
Yeah, 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 yeah. All right, guys, I think it's time for us to take a break. It's 4 o'clock now. Let's take a break of 15 minutes and then we will continue. Okay, so that is a demo, and I'm going to share you more details about Seldon-core. So let's start in another 15 minutes. Thank you, guys. See you in 15 minutes. Hi all, I'm back. So let's continue. All right. Oh my God. Okay. All right. So this is the end-to-end model serving, how the model serving works with Seldon-core, how Seldon-core helps in converting a machine learning model into a deployable microservice. Not only that, Seldon-core also exposes custom metrics from the models at a single endpoint, so that Prometheus can scrape the metrics from all these models from a single endpoint. And in addition to metrics, it also supports creation of graphs. These graphs are essentially tweaking the way inference requests have to be processed. So if there is a request that comes into the model, you can actually dictate in the Selden deployment manifest how this request has to be processed. If at all this request has to be fed into multiple models or fed into certain transformations before the request is actually sent to the actual model. So those things will be internally taken care by Selden itself. That is with the help of orchestrator. Okay, sorry. That is with the help of orchestrator. So laser pointer. So this is the orchestrator. Okay. So these are some of the advantages or the additional capabilities that come with using Selden code. Okay. But at the end of the day, you should still remember that uh, underneath what is really happening is there is a model server, right? There is a model server which is in the form of a Docker image, and this model server is actually consuming this model as a volume mount. So if you just look at this container alone, it is actually nothing but an microservice, our traditional microservice. But Selden Core actually abstracts away all these other intricacies of developing, of converting the converting the model into a microservice, and it gives you with certain other inbuilt features. So that is the advantage of using Selden Core. Okay, now let me introduce you to another concept in Seldon-core. This is called as reusable versus non-reusable model servers. Okay, actually the concept is very simple. In reusable model server, what happens is just refer to this diagram. This is the scenario that we saw in the previous slide. So there is an image registry. The Docker image of the model server resides in the image registry. There is a model that resides in an external central repository. And this is actually a reusable server. So if it is a scikit-learn model, then you can simply reuse the same server for any scikit-learn model. So if there are 10 different versions of the model available in the central repository, then the same server image is used. Only thing is all these different models are downloaded and then mounted into these server. So this results in low engineering effort from the software engineer. See, one image can serve many similar ML models. Okay, and not only that, Seldon Core itself provides certain reusable servers, readily available reusable servers. You can simply make use of those reusable servers. All you need to do is basically build your model using whatever framework for which the reusable server is available from Seldon. and then you don't have to necessarily build your own reusable server. You can simply make use of Seldon provided reusable servers. Okay. So these are reusable servers. Simply make use of the same container image again and again, depending on what is the type of model that you use. But whereas there is also another way of model serving in Seldon. This is called as non-reusable model servers. Okay. This will basically build the container image for each and every model. Okay. So there is an image registry. Okay. So this image registry, actually what it holds is, it holds the server as well as the model in a single image. Okay. So here it says, right, builds a container image that wraps the model functionality every time the model is trained. Okay. So every time the model is trained and a new version of model is available, rather than storing the model in an S3 bucket, you have the model in your source code repository itself. Okay. You just use your CI/CD pipeline to build the model from the source code repository, and then you can use Docker's multi-stage builds to produce this container image, to produce this non-reusable server. So the disadvantage here is that every time you produce a new version of the model, you have to build a new version of the Docker image. Okay. But nevertheless, both these approaches are useful and relevant in different contexts. Okay. So sometimes what happens is, you may have some certain organizational policies wherein you won't have access to an centralized repository like this. Okay. So you will have only access to a single Docker registry. So in that case, the only solution is to use non-reusable model servers. Okay. And there is also a performance advantage in using non-reusable servers, because in the reusable model servers, the model is actually stored in a volume. So if the volume is actually attached directly to the worker node, then the performance is really good, right? But remember, if it is a remote volume, okay, if the actual storage is actually remote, okay, then naturally there is a little bit of throughput uh, performance bottleneck that you may have to encounter when using a reusable server. Okay. So in situations where performance is paramount, you can never tolerate any degradation in the performance, then naturally it is better to use a non-reusable model server where the model is available as one of the layers in the Docker image itself, rather than being available on a volume mount, right? Because when you do a volume mount, then you are relying on the storage driver, then you are relying on what type of file system is used. So all these things will actually determine the performance of accessing the model from the server. So in situations like that, you will have to use non-reusable model servers. So that's why we say that both are useful and relevant in different contexts. Okay. Fine. So I'm going to continue. Right. So this is where I'm going to actually delve deeper into the Seldon deployment CRD itself. Let me maximize this window. Okay. So this is a sample Seldon deployment manifest. So this is the API version that is actually defined for the CRD. It is called as machine learning.seldon.io. So when do I actually create a Seldon deployment? So whenever I need to deploy a model, I create a Seldon deployment manifest. Okay. So in this scenario, what I'm going to do is I'm going to actually create a deployment like this. Okay. So here you see it's not a very simplistic single model deployment. Okay. So here you see that there are actually two models. Okay. So in this deployment, there are actually two models. So one is my hyphen model. Okay. This is a model. Okay. And then there is another model called as classifier. Okay, so in this example, the classifier is actually deployed using a reusable server, whereas my model is a non-reusable server, which means the model is actually embedded in the Docker image itself. Okay, just to give some differences. Okay, so there are two models. So my model is a non-reusable server, whereas the classifier model is a reusable server. Okay, and apart from these two models, this model deployment also has transformer. Okay, and also a combiner. Okay, so a transformer, basically what it does is, in the scenario, it will actually transform the input. So that's why it is called as input transformer. Okay, so whatever input that I send to this deployment, so this Seldon deployment, so that will be actually transformed, okay, by the input transformer, and then it will be fed to both the models. So the same transformed input is given to both the models, and then the output of these models is combined. Okay, so that is called as the combiner. So these are again, Docker images. So model combiner, it's your own logic. So you can write your own logic in your own programming language, build a Docker image out of it. Similarly, input transformer is the same thing. You write your own logic on how to transform the input, and then build a Docker image out of that and store it in an image registry. Similarly, store the model combiner in an image registry. Similarly, in this case, my-model is a non-reusable, my-model is an non-reusable server. So in this case, this also resides in an Docker registry, whereas classifier is a reusable model server. So the classifier model resides in a Google Cloud Storage, in this case, bucket. Okay, and then we are using actually Seldon's own inbuilt server. We are not building our server ourselves, so we are using the server that is provided by Seldon itself. Okay, so this is the deployment that we want to achieve. Okay, I want to achieve a model deployment like this. Okay, so this is the orchestrator. So this is basically the orchestrator that Seldon by default brings in whenever it deploys a model. So given this requirement, so let's say this is our requirement, and for this requirement, this is how the Seldon deployment manifest will look like. Okay, so here, as I said, there are three container images required: one for the input transformer, second for the my-model, and third for the model-combiner. So I have defined all these three images here. Okay, and then I proceed with defining the graph. So the graph will actually tell Seldon how the inference requests have to be processed. Okay, so to which component the request has to go in first, and then the output of that component, to which components the output has to go. So all those things will be defined here. Okay, so what I'm defining here is the very first container that will actually intercept the inference request is the transformer, because that is what we need here, right? The transformer has to actually get the input. So that is what we are defining here. And then we are defining defining multiple children. So in this case, we are defining one child, which is actually the combiner. So the combiner has two children because it combines the output of these two containers, which is my model and then the classifier. Okay, so the combiner has two children. So you see, which means the combiner will take the output from these two containers. Okay, it will take the output from these two containers and then combine them. Okay, so this is the way that you define the graph for our requirement. So I repeat again, this is the requirement. So we need an input transformer, and then the input transformer should send the output to both the models, and then the outputs from each of these models will have to be sent to the combiner. So the combiner will then send the response. Okay, that is the requirement. So for this requirement, so I need to define 3 container images. So I define all the 3 container images here. And then in the next step, I define the graph. So the first point within the graph is the transformer. And then the next is underneath the transformer, there is a single child, which is a combiner. This combiner is actually built using 2 different children. Okay. So this is a way to denote that this combiner has to combine the outputs from these 2 servers. Okay. This is actually a scikit-learn server, and this is our own model server. Okay. Okay, good. Okay, any questions, guys? I think it's clear. Okay, what I'll do is before, okay, there is only one more slide. I'll complete that slide and then go to the demo. This is the service orchestrator. So we were actually talking about this orchestrator, right? So basically this shows you in more detail what is the purpose of the service orchestrator. Okay. So in this case, the user sends the inference request to the deployment, to the Seldon deployment. Okay. So what happens is the service orchestrator will actually receive that request from the request. So the whatever request is sent by the user is it first goes to the service orchestrator. It doesn't directly goes to the models here. Okay. It directly goes to the service orchestrator. The service orchestrator reads the inference graph that we define in the Seldon deployment manifest. And based on how we have defined the graph, the service orchestrator passes the request accordingly. So in this case, the service orchestrator passes the request to the classifier model, gets the output, and then again sends a fresh request to the classifier 2 model, gets the output, and then this final output from classifier 2 goes back to the user. Okay, that is how the graph has been designed. So the whatever input the user provides, that is actually sent to classifier 1, and whatever output sent by the classifier 1 is actually passed on to classifier 2, and the output from classifier 2 is actually eventually sent back to the user. Okay, so these kind of defining your own flows or defining your own inference graphs is possible only because of the service orchestrator. Okay, the service orchestrator makes sure that it is basically the orchestrator that executes the graph. Okay, whatever rules that you specify or whatever sequence that you specify within the graph section of the Seldon deployment is actually executed by the service orchestrator. Okay, so this is the service orchestrator is by default, it will be injected into the pod. So you don't have to write any specification for the orchestrator. So the orchestrator is actually provided by Seldon itself. Okay, you don't have to worry about the orchestrator. Okay, so this is a very simplistic view of model deployment in Kubernetes using Seldon-core. Okay, so I am going to actually jump on to the demo, but before that, if there are any questions, please feel free to ask those questions. So we are going to start with the demo. All right, so fine. So let me start with the demo. Okay, what is this? All right, so I'm actually connected to a remote cluster. So let me see the namespaces. So I have a namespace called a Seldon-system. So I'm going to install Seldon-core. So I'm going to first of all install the Seldon-core controller into this namespace. Okay. So let me open up the Seldon-core documentation. So the Seldon-core actually comes as an Helm chart. So I'm going to basically use this Helm chart to install the Seldon-core. So I'm going to copy this command. So this actually installs the Seldon-core operator from this repository, from this Helm repository. So there is, it installs it into the namespace Seldon-system. I'm actually configuring usage metrics.enabled is equal to true, so that it will generate the metrics. Okay. So let me add the hyphen debug flag so that we can see what is actually going on. So I have given the command, so it is going to install the Seldon-core operator inside the Seldon-system namespace. So the installation is completed. So let me see the pods. Good. So the Seldon operator is successfully installed, and here you will see the controller running. Okay. So the Seldon core is successfully installed, which is good. So this is a typical Kubernetes controller. Okay. So it will watch for Seldon deployments, and then it will create the necessary Kubernetes resources. Okay. So in the next step, what I'm going to do is I'm going to switch over to the Seldon namespace. So I have created another namespace called as Seldon. So I will be actually deploying the models into this namespace. Okay, Seldon-system will have the Seldon core operator, but whereas I want the models to be deployed into this namespace. Okay, so I need to create a Seldon deployment. So I already have a Seldon deployment created. Okay, so this is the Seldon deployment that I'm going to use. This is a very simple Seldon deployment manifest. Okay, so if you see the specification, this is again a very simple graph. So this graph actually has a single model. Okay, and this is actually a reusable server model. So this uses the Seldon's scikit-learn server. So which means I don't have to build my own server image at all. So I am going to reuse the Seldon's scikit-learn server. And my model, I'm going to actually reuse one of the example models that Seldon Core provides. It actually resides in a Google Storage bucket. So this is the location of the model. Okay. And I'm actually giving the name classifier. Okay. So it's a very simple model deployment that I'm going to show. So now once I am ready with the Seldon deployment manifest, I'm going to actually apply this manifest. Okay. Okay, so the manifest is applied. So let's see what are the pods. So there is one pod that is running, which is good. So there is only one model as part of this graph. So what has happened is Seldon controller has read the Seldon deployment and it has created a pod. And this pod is also in ready state now. So you see both the containers of the pods, both the containers of the pod are up and running. Now let's describe the pod and see the contents. So what is there within the pod? So let's take a look at what are the contents of this pod. So there is one init container. Okay. So it's called as classifier model initializer. So this is the init container that actually what it does is basically it fetches the model. So if you see here, this is the argument that is passed. Okay. So this model is actually fetched from the Google Storage bucket, and then it is mounted onto this volume, mounted onto this mount path. Okay. That is actually done by the init container. Okay. So next, let's see what are the other two containers running. Okay. So the next container that is running is the Seldon-core executor. This is nothing but the orchestrator. Okay. So the orchestrator is running, and then finally, let's see what is the third container. Third container, I think just now we saw this executor. So where is the model container? I'm actually looking for the, here is the model container. So this is actually the model server. Okay. If you see, it is actually using the image SKLane server. Okay. Because in the, if you see in the deployment, oh, sorry, not this. If you actually see the, if you actually remember the Seldon deployment that I showed you, actually it used Seldon's sklearn server. Okay. So the image basically is Seldon provided scikit-learn server. Okay. And there is another container which is nothing but the service orchestrator. Okay. So two containers are running. Good. So now we have successfully deployed our model onto Kubernetes. So we have verified that the model is successfully running. Okay, so if I see kubectl get pods, so the model is successfully running. Now I'm going to send inference requests. Okay, I'm actually going to invoke the model. Okay, so I'm going to actually expose the service. Okay, so rather than using Istio or Ambassador, so for this demo, I'm going to actually use kubectl port forward to expose the service. Okay, so it has created two services. Okay, so this service actually, there is the first service, first cluster IP service. This first cluster IP service actually points to the orchestrator. Okay, and the second service actually points to the model container, the model server. Okay, but we need to actually send the invocation request, the inference request to the orchestrator. So what I'm going to do is kubectl port forward service. So I'm going to port forward this service. So the target port is 8000. Okay, this is the target port. So I'm actually doing a port forward here. Okay. Okay, fine. So now I'm ready to send REST API calls to the model. Okay, so I will open another tab here, and I have already the request. This is the request that I'm going to send. But before that, I'll update the port number. I'll just explain the request. The port number is 56647. So I'm going to actually send a predict request to the model. But if you notice, I'm actually not directly sending the request to the model. I'm actually sending the request to the orchestrator. Okay. So this is the port at which I have port forwarded onto my local machine. So I'm actually sending, this is the endpoint. Okay. The service orchestrator actually exposes the model at this endpoint, API slash v1.0 slash predictions. So I'm actually sending a JSON content. Here you see content type is JSON, and actually I'm sending form data. Okay, so if you see -d, I'm actually sending JSON, the form data. So this is the data that I am sending. I'm actually sending a JSON, so you don't have to worry about what is actually I'm sending an ND array, which is basically a Python object. Okay, so internally the model will read this ND array, and then it will, based on what I'm sending in the ND array, it will give me the prediction output. Okay, and finally I'm using JQ to parse the output, to parse the response. So let's see what happens. So this is good. So basically it gives me the output. Okay. So this is the output that it has generated. And also it gives me some metadata. Okay. It says that the response is actually coming from this model, which is classifier. And this is the image that is used in the model. So what is really happening here is I have actually deployed the model. Now I am sending input to that model. See, I'm actually sending an ND array, but this is a very simplistic way of invoking the model. So in practical scenarios, you will have more advanced ways of invoking the model. Okay. So I'm sending a request and I'm getting a response. Okay. So this response actually comes from the model. Okay. Um, because you can see it here. You can see which model actually has sent this response, because it is actually, this is the model that is actually in the request path. So the model, so here you see that this is the only model that was in the request path, because we, in our deployment, we have only one model. So this was in the request path, and the response has actually come from this model. Okay, we can perhaps send the request again. Yeah, and again I'm getting a response. Okay, sure. So that is all, guys. So it was we installed Seldon-core, and then we exposed the Seldon-core orchestrator using using port forward, and then we sent an inference request to the deployed model, and then we get a successful output. Okay, so we have finished the session. So are there any questions? So let me stop the sharing. All right then. So if there are no questions, thank you guys. Thank you for joining the session. Hope it was useful, and hope to see you all in KCD Chennai next month on the 22nd. Okay. Okay. There is a question from Prudvi. What are the differences between Kubeflow and Seldon-core? Yeah. See, Seldon-core only is responsible only for model serving. Okay. It won't be useful in other phases of the model development lifecycle. Whereas Kubeflow provides you with all the remaining pieces of the model lifecycle. So Kubeflow also provides you with pipelines. Kubeflow also provides you with its own serving framework. Kubeflow provides you with notebooks for developing models. So that is the difference between Seldon-core and Kubeflow. Okay, so Kubeflow is a larger system than Seldon-core. Seldon-core is responsible only for the serving of model, which is model deployment and monitoring. Okay. Okay, guys. Thank you so much for joining the session. Bye-bye. Have a nice weekend. Bye.
Thank you, Senthil. This informative session. Thank you so much.
Thank you. Bye.